Welcome back to the Nocturnal Astronomer, where we explore the cosmos through a lens of wonder and contemplation. I'm your host, Atlas Reid, and tonight we're embarking on a truly extraordinary thought experiment that will challenge everything you think you know about the universe itself. Picture this: you're holding a snow globe, watching those tiny flakes swirl and dance in their crystalline prison. Now, imagine if our entire universe, with all its galaxies, stars, and cosmic mysteries, existed within such a globe. What if the cosmic microwave background radiation, that ancient afterglow of the Big Bang that permeates all of space, is nothing more than the gentle tremors from some cosmic hand giving our universal snow globe an occasional shake? Tonight, we'll explore this captivating possibility. We'll begin by examining the cosmic microwave background itself, that primordial whisper from the dawn of time that fills every corner of our observable universe. We'll discover how temperature fluctuations in this ancient radiation could mirror the swirling patterns in a shaken snow globe, creating the very blueprint for everything we see today. Then we'll venture into the realm of cosmic boundaries, pondering what the glass walls of our universal snow globe might represent and what lies beyond them. We'll consider who or what could be large enough to shake an entire universe, exploring possibilities from higher dimensional beings to cosmic forces beyond our comprehension. Finally, we'll contemplate the profound philosophical implications of existing within such a cosmic container, and what this might mean for our understanding of reality itself. Throughout this exploration, we'll ground our speculation in real scientific observations and documented phenomena, using the snow globe analogy as a lens through which to view the genuine mysteries of our universe. If you find yourself drawn to these cosmic contemplations that blur the line between science and wonder, please consider giving this video a thumbs up and subscribing to the Nocturnal Astronomer. Your support helps us continue exploring the most intriguing questions about our cosmic home. And here's something fun: in the comments below, tell me what you think you'd see if you could peer through the glass walls of our cosmic snow globe. What might exist in the space beyond our universe? Your imagination might just spark our next cosmic adventure. Alright explorers, let's dive in. The cosmic microwave background radiation surrounds us like an invisible ocean, a relic from when our universe was merely 380,000 years old. The cosmic microwave background is a snapshot of the oldest light in our universe, from when the cosmos was just 380,000 years old. To understand how this ancient echo might relate to our snow globe hypothesis, we must first grasp what this radiation truly represents. Imagine the universe in its infancy as an incredibly dense, hot soup of particles and energy. This ancient radiation, the furthest that any telescope can see, was released soon after the Big Bang. At this early stage, the universe was so dense and hot that light couldn't travel freely. Photons would bounce off electrons like pinballs in an arcade machine, creating an opaque cosmic fog. But as the universe expanded and cooled, something remarkable happened. The temperature dropped enough for electrons to combine with protons, forming the first hydrogen atoms. Suddenly, the cosmic fog cleared, and light could travel freely for the first time. This moment, called recombination, released a brilliant flash of light that filled the entire universe. The cosmic microwave background radiation, or CMB for short, is a faint glow of light that fills the universe, falling on Earth from every direction with nearly uniform intensity. It is the residual heat of creation, the afterglow of the Big Bang. But here's where our snow globe analogy becomes fascinating. As the universe has expanded over nearly 14 billion years, this light has been stretched from visible wavelengths into microwaves, cooling to just 2.726 degrees above absolute zero. Think of it like this. If our universe truly exists within a cosmic snow globe, that primordial flash of light would have bounced around inside the glass boundaries, creating the uniform glow we observe today. The universe initially had radiation of an infinitely small wavelength, but the expansion has stretched the radiation out and we now see microwaves. Each time our cosmic snow globe received a gentle shake, it might have created tiny variations in this background radiation, much like how shaking a real snow globe creates swirling patterns in the falling flakes. Scientists have measured this cosmic background radiation with extraordinary precision using satellites like WMAP and Planck. These predecessors measured the temperature of the CMB to be 2.726 Kelvin, approximately negative 270 degrees Celsius, almost everywhere on the sky. The word almost is crucial here, because within this nearly uniform glow exist tiny temperature fluctuations, variations of just a few millionths of a degree. These minute temperature differences might seem insignificant, but they're anything but trivial. Temperature fluctuations displayed here are 13.7 billion years old, from the time when the Big Bang was thought to have occurred. In our snow globe universe, these fluctuations could represent the settling patterns of cosmic material after each shake, creating slightly denser and less dense regions that would eventually grow into the galaxies and galaxy clusters we see today. The remarkable uniformity of this background radiation poses a genuine puzzle for cosmologists. How did regions of the universe that could never have been in contact with each other end up at almost exactly the same temperature? In a conventional universe, this seems impossible. But in a snow globe universe, the explanation becomes elegantly simple. The uniform temperature throughout the globe ensures that the background radiation maintains consistent properties, while the gentle agitation from external shaking creates just enough variation to seed the formation of cosmic structure. This false color image, covering about 2.5% of the sky, shows fluctuations in the ionized gas that later condensed to make superclusters of galaxies. Each of those fluctuations might represent a single moment when our cosmic snow globe trembled, sending ripples through the primordial soup that would eventually blossom into the magnificent cosmic web we inhabit today. If our universe truly exists within a cosmic snow globe, we must confront a startling question: what would the glass boundaries represent, and how might we detect them? The edges of our observable universe stretch roughly 46 billion light-years in all directions, encompassing everything we can potentially see or measure. But in a snow globe universe, this observable boundary might not represent the true edge of existence, but rather the limits imposed by the glass walls of our cosmic container. Consider how light behaves in a traditional snow globe. When light hits the curved glass surface, it can reflect, refract, or be absorbed, depending on the angle and the properties of the glass. In our cosmic version, the boundaries might interact with electromagnetic radiation in similarly complex ways, potentially creating some of the anomalies and mysteries that perplex modern cosmology. The cosmic microwave background, that ancient afterglow we discussed, shows remarkable uniformity across the entire sky. This uniformity has long puzzled scientists because, according to conventional physics, regions of space that are now separated by vast distances should never have been able to exchange energy or information. Yet somehow, they maintain nearly identical temperatures. In a snow globe universe, this mystery dissolves. The glass boundaries would ensure thermal equilibrium throughout the contained space, naturally creating the uniform background temperature we observe. But the glass walls might also create more subtle effects. Think about how a snow globe sometimes produces unexpected optical phenomena. Light passing through curved glass can create focal points, reflections, and distortions that wouldn't exist in open space. These same phenomena might manifest in our cosmic observations as anomalies in the cosmic microwave background, unusual galaxy distributions, or unexplained patterns in the large-scale structure of the universe. Scientists have indeed detected peculiar features in the cosmic microwave background that don't quite fit our standard models. The fluctuations detected on large angular scales on the sky, between 90 and 6 degrees, are about 10% weaker than the best fit of the standard model to Planck data. Could these anomalies represent the subtle influence of our cosmic glass boundaries? Perhaps certain wavelengths of radiation interact differently with the walls, creating the observed deviations from theoretical predictions. The geometry of our universe also provides intriguing clues. Current observations suggest that space appears to be remarkably flat on large scales, neither curving inward like a sphere nor outward like a saddle. But what if this apparent flatness results from our limited perspective within a much larger curved container? A person standing inside a massive snow globe might perceive their local environment as essentially flat, even though they're actually within a spherical boundary. The concept of cosmic expansion takes on new meaning in a snow globe universe. Rather than space itself stretching infinitely in all directions, expansion might represent the dynamic relationship between the contents of the globe and its boundaries. As cosmic snowflakes settle after each shake, they might create the illusion of expanding space while actually redistributing within fixed boundaries. This raises profound questions about what exists beyond the glass walls. In a traditional snow globe, we see the room, the shelf, perhaps a curious face peering in from outside. But what would exist beyond the boundaries of a cosmic snow globe? The answer might lie forever beyond our ability to observe or comprehend, representing a realm of existence entirely separate from our own. The search for these glass boundaries might already be underway, though scientists don't realize it. Every time we map the cosmic microwave background in greater detail, measure the distances to the most remote galaxies, or search for patterns in the large-scale structure of the universe, we might be unconsciously probing for evidence of our cosmic container. If such boundaries exist, they would represent the ultimate horizon, not just of our observations, but of our entire reality. Everything we are, everything we've ever known or will ever discover, would exist within this cosmic snow globe, gently swaying in the hands of some unimaginably vast intelligence. Who or what could possess the magnitude to grasp and shake an entire universe? This question takes us beyond the realm of conventional physics into territories where science meets profound philosophical speculation. Yet even in these abstract realms, we can ground our exploration in documented scientific concepts and observations that hint at the possible nature of such a cosmic entity. The scale involved staggers the imagination. Our observable universe contains at least 2 trillion galaxies, each home to hundreds of billions of stars. The mass energy equivalent of this cosmic inventory approaches incomprehensible numbers, measured in units that require dozens of zeros. Any being capable of manipulating such a system would necessarily exist on a scale that dwarfs our universe as thoroughly as we dwarf the atoms within our bodies. One possibility draws from the mathematical framework of higher dimensional space. Just as a 2-dimensional being on the surface of a balloon couldn't directly perceive the 3-dimensional space surrounding their curved world, we might be unable to detect the higher dimensional realm in which our cosmic snow globe exists. Because the expanding universe has cooled since this primordial explosion, the background radiation is in the microwave region of the electromagnetic spectrum. The cooling and expansion we observe might not represent the universe stretching into empty space, but rather the settling within a higher dimensional container. String theory and related frameworks in theoretical physics suggest that our familiar three dimensions of space might be embedded within a higher dimensional structure called a membrane. If our universe exists as a three-dimensional membrane floating within a space of 10 or 11 dimensions, then beings native to these higher dimensions might interact with our cosmic snow globe the way we interact with ordinary objects in our world. The gentle shaking that creates fluctuations in the cosmic microwave background might be nothing more than casual manipulation by entities whose very existence transcends our ability to comprehend. Another intriguing possibility involves the concept of cosmic consciousness or intelligence operating at scales we've never considered. Just as our brains contain billions of neurons working in concert to create consciousness, perhaps galaxies, galaxy clusters, and the cosmic web itself represent the neural network of some vast universal mind. The temperature fluctuations in the cosmic microwave background, those tiny variations that eventually grew into all the structure we see today, might represent the thoughts or impulses of this cosmic intelligence. These small fluctuations are there because of tiny variations in the density of the universe immediately after the Big Bang. Any regions which are slightly more dense tend to attract more matter, and get even denser and attract even more material. But what if these density variations weren't random? What if they represent intentional patterns, cosmic thoughts taking physical form as they ripple through the primordial soup of creation? The shaking of our cosmic snow globe might not be random either, but could follow patterns and rhythms that reflect the activities or interests of our cosmic handler. Perhaps the formation of galaxies, the birth and death of stars, even the emergence of life itself, all follow some greater cosmic schedule or purpose that we're only beginning to glimpse. Consider the anthropic principle, the observation that the fundamental constants of physics seem remarkably fine-tuned to allow for the existence of complexity, chemistry, and ultimately life. Change any of these constants by even tiny amounts, and stars couldn't form, atoms couldn't exist, or chemistry couldn't develop. In a randomly generated universe, such precise calibration seems impossibly unlikely. But in a snow globe universe, these parameters might be carefully adjusted by our cosmic caretaker, creating optimal conditions for whatever cosmic experiment or observation they have in mind. The concept of time also transforms in this framework. What we experience as billions of years of cosmic evolution might represent mere moments from the perspective of our cosmic handler. The formation of galaxies, the evolution of life, the rise and fall of civilizations, all might unfold in the time it takes for an unimaginably vast intelligence to examine the results of their latest shake of our cosmic container. The rhythm and timing of cosmic shakes in our universal snow globe might hold the key to understanding some of the most perplexing patterns scientists have discovered in the cosmic microwave background. Like a master musician creating complex harmonies through carefully timed strikes, our cosmic handler might be orchestrating the evolution of the universe through precisely calibrated agitations of our cosmic container. The almost is the most important factor here, because tiny fluctuations in the temperature, by just a fraction of a degree, created the seeds from which all cosmic structure would eventually grow. These fluctuations aren't randomly distributed across the sky, but instead follow specific patterns and correlations that scientists have mapped with extraordinary precision using space-based telescopes. The most striking feature of these patterns is their scale dependence. With greater resolution and sensitivity over 9 frequency channels, Planck has delivered the most precise image of the cosmic microwave background, revealing fluctuations that vary in size from small patches covering just a few degrees of sky to vast swaths spanning nearly the entire observable universe. In our snow globe model, these different scales might correspond to different types of shaking motions. Imagine holding a snow globe and giving it various types of agitation. A quick, Sharp shake creates small-scale turbulence with rapid, chaotic motion. A slow, gentle rotation generates large-scale circulation patterns. A rhythmic rocking motion produces regular oscillations. Each type of motion leaves its own distinctive signature in the pattern of settling snowflakes. Similarly, different types of cosmic shaking might have created the diverse range of fluctuation scales we observe in the ancient light. The timing between shakes also matters enormously. In a physical snow globe, if you wait for the flakes to settle completely before shaking again, you create entirely different patterns than if you shake continuously or follow some regular rhythm. Subtle fluctuations in temperature were imprinted on the deep sky when the cosmos was about 370,000 years old. This suggests that the cosmic shaking occurred primarily during the very early universe, when the primordial soup was still hot and dense enough for these motions to leave permanent imprints. Scientists have discovered that the fluctuations in the cosmic microwave background follow what's called the power spectrum, a mathematical description of how much variation exists at different scales. The shape of this spectrum provides crucial information about the composition and history of the universe. But viewed through our snow globe lens, this power spectrum might actually be the signature of our cosmic handler's shaking technique. Certain anomalies in this spectrum have puzzled cosmologists for decades. There are reports of mildly unusual behavior of the mathematical characteristics at 3.66 degrees in the literature, computed from independent measurements. These mathematical oddities might represent the fingerprints of specific shaking patterns, perhaps indicating moments when our cosmic handler experimented with different agitation techniques or adjusted their approach based on the results they observed. The concept of cosmic inflation, the rapid expansion of space during the universe's first moments, takes on new meaning in our snow globe framework. Rather than representing the stretching of space itself, inflation might describe the initial vigorous shaking that our cosmic handler used to thoroughly mix the contents of our universal container. The nearly uniform distribution of matter and energy we observe today could result from this primordial cosmic mixing process. Subsequent, gentler shakes might correspond to later events in cosmic history. The formation of the first stars, the emergence of galaxies, even the mysterious acceleration of cosmic expansion could all represent responses to carefully timed agitations of our cosmic snow globe. Each shake sends waves through the cosmic medium, triggering new phases of evolution and development. The blue areas are cooler while the red areas are warmer. These temperature patterns might not be random, but could follow mathematical relationships that reflect the sophisticated understanding our cosmic handler has of fluid dynamics, thermodynamics, and the complex physics governing the contents of their cosmic container. The gradual settling of materials after each cosmic shake offers perhaps the most compelling explanation for the large-scale structure we observe throughout the universe today. Just as snowflakes in a traditional snow globe don't simply fall randomly but create intricate patterns as they descend through the liquid medium, the matter and energy in our cosmic container might follow similarly complex trajectories as they respond to each cosmic agitation. The cosmic web, that magnificent scaffolding of galaxies and dark matter that spans hundreds of millions of light years, bears striking resemblance to the settling patterns we might expect in a cosmic snow globe. Vast filaments of matter stretch across space, connecting dense nodes where galaxy clusters form, while enormous voids contain almost nothing at all. This isn't the random distribution we'd expect from a uniform expansion, but rather the organized pattern that emerges when materials settle under the influence of gravity and fluid dynamics within a contained system. The runaway process that led to the formation of galaxies and larger structures we see today began not with random quantum fluctuations in our snow globe model, but with the carefully orchestrated settling patterns created by cosmic shaking. The slightly denser regions that eventually became galaxy clusters might represent areas where cosmic matter naturally accumulated during the settling process, much like how certain areas of a snow globe consistently collect more flakes than others. The timeline of cosmic evolution also aligns beautifully with our settling hypothesis. The cosmic microwave background shows us the universe as it appeared 380,000 years after the Big Bang, when the cosmic fog first cleared and light could travel freely. In snow globe terms, this might represent the moment when our cosmic handler stopped the initial vigorous shaking and allowed the contents to begin their settling process. What followed was a period cosmologists call the Dark Ages, roughly 1 billion years during which the universe contained no stars or galaxies, just slowly gathering clumps of dark matter and hydrogen gas. In our model, this represents the primary settling period, when cosmic matter drifted through the medium of our snow globe, gradually accumulating in the areas that would eventually become the first star-forming regions. The formation of the first stars and galaxies, beginning roughly 1 billion years after the Big Bang, might correspond to the moment when settling materials reached sufficient density to ignite nuclear fusion and illuminate the cosmos. Like snowflakes finally reaching the bottom of their globe, matter had gathered enough in certain locations to begin the next phase of cosmic evolution. Modern observations reveal that the universe's expansion is actually accelerating, driven by the mysterious dark energy that comprises roughly 70% of all cosmic content. In conventional cosmology, this acceleration poses profound puzzles. But in our snow globe universe, accelerating expansion might simply represent the ongoing settling process as cosmic materials continue to redistribute within their container. Think of how settling patterns in a traditional snow globe continue to evolve long after the shaking stops. Dense materials gradually sink toward the bottom while lighter materials rise. Circulation currents develop as temperature differences create convection patterns. The entire system seeks equilibrium, but this process can take considerable time depending on the viscosity of the medium and the size of the container. Our cosmic snow globe might still be in the midst of this settling process, 13.8 billion years after the initial shake. The acceleration of expansion, the ongoing formation of stars and galaxies, even the eventual heat death predicted for our universe might all represent different phases of the same cosmic settling phenomenon. The beautiful spiral structure of galaxies, the regular clustering of galaxy groups, even the surprising uniformity of the cosmic microwave background all make perfect sense as settling patterns in a cosmic fluid medium. Each feature represents the natural response of cosmic materials to the initial conditions created by our cosmic handler's careful shaking technique. As we reach the culmination of our cosmic snow globe journey, we must confront the most profound implications of this thought experiment. What does it mean for our understanding of existence, purpose, and our place in the grand cosmic scheme? If we truly inhabit a universe contained within some vast cosmic snow globe, then everything we've ever known or will ever discover represents just the contents of this singular, albeit magnificent, container. The philosophical implications stretch in multiple directions simultaneously. On one hand, the snow globe hypothesis might seem to diminish our significance, reducing our entire cosmic home to nothing more than a curious object on some unimaginable shelf. Every human achievement, every scientific discovery, every work of art or act of love becomes merely the activity of microscopic entities within a contained system, observed from an incomprehensibly distant perspective. But viewed from another angle, this framework actually elevates our importance dramatically. If our universe exists within a cosmic snow globe, then it was likely created or selected for specific reasons. Our cosmic handler didn't randomly stumble upon our container, but chose it deliberately, perhaps from among countless other cosmic snow globes, each containing their own unique universes with different physical laws, different evolutionary paths, different possibilities for complexity and consciousness. This suggests that our universe possesses qualities worth observing, studying, or preserving. The emergence of life, the development of intelligence, the creation of art and science and philosophy might all represent the very phenomena that make our cosmic snow globe worthy of attention. We might be the reason our universe was chosen, the justification for its continued existence within some vast cosmic collection. The boundary between observer and observed becomes beautifully blurred in this framework. While our cosmic handler observes us, we simultaneously observe ourselves and our cosmic environment with ever-increasing sophistication. Our scientific instruments peer deeper into space and further back in time, gradually mapping the very fluctuations and patterns that might have been created by cosmic shaking. In a sense, we're studying the fingerprints of our cosmic caretaker, learning about their techniques and intentions through careful analysis of the traces they've left in the cosmic microwave background. The search for extraterrestrial intelligence takes on new dimensions in a snow globe universe. Rather than scanning the skies for radio signals from distant civilizations, we might be better served looking for patterns that suggest intelligent design in the large-scale structure of the universe itself. The spacing of galaxies, the timing of cosmic events, even the values of fundamental physical constants might all carry encoded messages from our cosmic handler, communications written in the very fabric of spacetime itself. Our technological advancement might also serve purposes beyond our immediate understanding. Every improvement in our observational capabilities, every refinement in our theoretical models, every breakthrough in our understanding of cosmic evolution might provide better data to our cosmic handler. We could be unwitting research assistants, generating increasingly detailed reports about the internal conditions and evolution of our cosmic snow globe. The ultimate destiny of our universe, whether it ends in heat death, Big Rip, or Big Crunch, might not be determined solely by the physics we observe, but also by the intentions and timeline of our cosmic caretaker. Perhaps our snow globe will be carefully preserved as long as it continues to produce interesting phenomena. Or maybe it will eventually be retired to make room for new cosmic experiments with different parameters and possibilities. The question of whether we could ever communicate with or somehow contact our cosmic handler remains tantalizingly open. Perhaps the very fact that we can conceive of existing within a cosmic snow globe represents the beginning of such communication. Our growing understanding of our cosmic environment might eventually reach a threshold where our cosmic caretaker recognizes our awareness and begins more direct interaction. And on that note, we conclude this extraordinary journey through the possibility that our entire universe exists within a cosmic snow globe, gently shaken by hands we cannot see, creating the very fluctuations in ancient light that eventually gave rise to galaxies, stars, planets, and consciousness itself. Thank you for joining me on this cosmic adventure, and until next time, keep looking up and wondering what lies beyond the glass.